Hello everyone, my name is Patrick, and I'm joined today by Daniel to talk to you about the concept of the state observer, more specifically known as the Luenberger Observer. The general goal of this kind of observer is to predict a system's response to an input using knowledge of the underlying process, making it a very appealing modeling approach when implementing process controls. We'll be considering linear dynamic systems modeled using the general state space model. This looks like the following. We have x dot equals ax plus b u and y equals cx plus d u. In this model, x is a vector that represents the internal state of the system, u is a vector of exogenous inputs to the system, and y is the vector of outputs. For many physical systems, it is useful to think of y as set measurements that are taken of the system's internal state. In practice, it may be prohibitively expensive or infeasible to measure every element of the system's internal state. In this scenario, the dimensionality of y, given as y is of p and x n, would be less than x, meaning p must be less than n. However, for the purposes of controller design, we may desire to be able to estimate the full internal state of the system. The idea of generating an estimate for the internal state of a dynamic system, given knowledge of only its inputs and limited sensor measurements or outputs, u and y, is the idea known as state reconstruction. The task of state reconstruction is performed by a dynamic system called a state observer. In this lecture, we will demonstrate the performance of a simple observer known as a Luenberger observer. The Luenberger observer for the system shown here has the following form. We have x hat dot equals a x hat plus b u. We tack on an extra term, L times u minus or y minus y hat, where y hat is cx hat plus d. Here, x hat represents the observer's estimate of the state, y hat is the observer's estimate of the output, and L is the design parameter, aka the vector we are trying to engineer. To understand how to choose the vector L, we need to understand the dynamics of the error, E, defined as the difference between the true state of the system, x, and the predicted state, x hat. We do this by writing the differential equation for E, denoted as E dot, as x dot minus x hat dot. Now some simple algebra you can plug in from the previous couple of equations. X dot is a x plus b u minus a x hat plus b u plus L times y minus y hat. This can be simplified down to a times x minus x hat plus L, and then we can substitute in the two y's, giving us cx plus d u minus cx hat plus du. And so finally, when you combine all these and realize that x minus x hat is simply E, we get the following expression for E dot as A minus LC times E. Now, let us consider the desired behavior of E of t. So, we would like for E to approach 0 as t grows infinitely large. This means pretty much that a predicted state in x minus x hat converges to the actual true state. This property will be satisfied when the state transition matrix A minus LC, seen here, is Hurwitz. Or in other words, when all of the eigenvalues have negative real components. Thus, our objective in designing the Luenberger Observer is to specify the vector L such that the matrix A minus L times C is Hurwitz.
Okay, now that Patrick has discussed the theory and principles behind designing Luenberger observers, I'd like to demonstrate an example of how we could model the performance of such an observer using Simulink. So for this example, I've taken a simple example of a system. This system is a mass spring damper system, which has a state consisting of two elements, the position and velocity of the mass. And we won't go through the derivation of the state space model in this lecture, but here I've just specified the appropriate A, B, C, and D matrices along with initial conditions. So this is saying that we begin by displacing the mass by 5 length units and letting it go from rest with 0 initial velocity. So this block here will compute the dynamics of our actual system given an single input U and a single output Y, which in this case is the position of the mass over time. And so what we're doing now is that we are taking U of t and Y of t and feeding them into this state observer. So let's click into this subsystem to see how we're modeling our state observer. So this here is all just the block diagram implementation of the equations that were presented previously. So you can recall that the time derivative of x hat is equal to a x hat plus bu plus L times y minus y hat. And for this example, I have specified our vector L using MATLAB's pole placement command in order to ensure that the dynamics of our error are decaying over time. And we then integrate the derivative of x hat to yield x hat and multiply by c to get our output y hat. And now we can simply feed these signals into our viewer in order to compare the actual output of the system to the predicted output, the output predicted by our state observer. And let's see what we get. All right, so here we have several curves. This one here represents our true output. So as expected, we begin at a displacement of 5, and over time we see a damped cosine behavior, which is what we would expect based on our physical intuition. And this here is the prediction of our observer. So we can see that it starts out with the wrong initial condition, but over time, our observer prediction gradually converges to our true result. And by the time we've reached around 12 time units, we can see that our predictions are virtually indistinguishable from the true system behavior.
In this video, we'll talk about the Heaviside expansion method to solve differential equations using Laplace transform. This method is a great alternative to the partial fraction method since the mathematics can get messy using the partial fraction. One question we might often be asked is to find inverse Laplace transform of Ys. The first thing we need to do is to identify all the roots of the denominator of the original function. Then we can rearrange function ys into different terms that will be easily taken inverse Laplace transform. Next, we need to solve for the unknown numerator. There are three equations that we can use to solve for the numerator. Depending on the characteristic of the root, if the root is not a repeated root, we can use the first equation. The second equation is used for repeated root with the highest order, and the third equation can be used for repeated root with lower order. For easier understanding, let's go over an example. In this example, we are asked to find the inverse Laplace transform of function ys equal s plus 2 over s cubed minus s squared minus 5s minus 3. The first step is also to find the root of the denominator and rearrange function ys. So we will have two roots, s minus 3, s equal 3, and s equal minus 1, which is a repeated root. Next step will be solving for each a, b, and c. We notice that s equal 3 is not a repeated root, so we could use the first equation. We plug in rk into this equation, and eventually we will get a equal 5 over 16. Next, we need to solve for b. This will be a bit trickier since s minus 1 is a repeated root, but this term does not hold the highest order, so we need to use equation 3 instead. In this case, rk equal minus 1, m is the order, equal 2, k run from 2 to m. In this case, k will be equal to 2. One mistake people often make is d is not a constant, but this is a derivation. Plug in all the parameters. Eventually you will get b equal to minus 5 over 16. Lastly, you need to solve for c. C over s plus 1 squared has repeated root, but it holds the highest order, so this time we will use equation 2. rk equal 1, m is still 2. Plug in the parameter, you will get c equal to minus 1 over 4. Now you know a, b, and c. You can describe ys as 3 separate terms, which can be easily taken inverse Laplace transform to y.